This video is about standing waves and resonance, and we're looking at specifically transverse waves on a string. We will get to other situations a little bit later, but for right now, let's stick with this. So maybe a good place to start would be an instrument. Let's try an upright bass. Okay, so maybe we've got an upright bass, and now we can look at a couple of different things. We've got these 4 strings on here. This one will be tuned to E1. Second string will be A1. Let's see, we'll go E1. A1 will be the second, D2, G2. And then we'll give these some frequencies. We have E1 is 41.2 Hertz. A1 is 55 Hertz, 55.0. D2 73.42. And G2 is 98. So we've got some frequencies. I would give mass lengths and tensions, except it doesn't make a whole lot of sense because the strings aren't always the same mass density. So we'll figure that part out afterwards. Let's find the fundamental wavelength on the E string. We can find the third harmonic wavelength on the A string. Maybe we can find the frequency of the fifth harmonic on the D string. So we've got a couple of things. Now we do need a little bit more information. And the big piece that we need is the length of the string. So the length of the string from here to here is about 105 centimeters, so 1.05 meters is that length. So let's give this a shot. If I am looking for the fundamental wavelength on an E string, I know that my wavelength, I have symmetric boundary conditions. This end is fixed, this end is fixed. So my wavelength is going to be 2L divided by N. Now I'm looking at the N equals 1 case, which means this N is also going to be 1. So I'm just going to get 2 times L. 2 times 1.05 meters gives me a wavelength of 2.10 meters. Next one, I want to find the third wavelength on the A string. Wavelength 3, 2L over 3. So I'm going to get a 2L. I'm going to get a 2 times 1.05 meters over 3, which is going to be equal to 0.70 meters. If I were to find the N equals 1 wavelength on the A string, because the length of the string is the same, it's going to be the same wavelength. So the frequency is going to depend on something else, and we'll get back to that in just a moment. If I want the fifth frequency on my D string, well, the fifth frequency, I know that my nth frequency is equal to N times my first frequency. So this is going to be 5 times 73.42 Hertz, which will be 367.1. that's going to be my 5th frequency. So once I have a couple of frequencies or a couple of wavelengths, this thing really isn't too bad. I'm just using some simple formulas. I'm using that my nth wavelength is just going to be 2L over N. I'm using that my nth frequency is going to be N times my fundamental frequency. But maybe I want to find a little bit more. Maybe what I'd like to find is, given a mass density for the string, I want to find a tension. So let's do that. Let's find the tension on G if the string that we're using for it is about 20 grams per meter, which is typical for this string. It's a whole lot lighter than the E string. I'll come back to that too. So if my mass density is 20 grams per meter, that means this is 0.020 kilograms per meter. I know my wave speed is the square root of tension divided by mu. And I also know that my wave speed is equal to a wavelength times a frequency. And I can do this with any n value, but being that I have my fundamental frequency for this guy already, I'm just going to use F1. So my lambda 1, 2L over 1, and I've already found that up here, that's 2.10 meters. Meters, yes. My frequency 1 was going to be 98 hertz, which means my wave speed, which is lambda times frequency, is 2.1 times 98, which is 205.8. So I get 205.8 meters per second. Plugging into here, if V is equal to square root of tension over mu, I'm looking for square root of tension. Well, I'm looking for just tension. So let me solve this. I'm going to square both sides. That part goes away. And I get that V squared equals tension over mu. So my tension must be mu times V squared, and I can plug in 0.02 kilograms per meter, 205.8 meters per second, and I've got to square that thing, and I get the tension in my string has to be 847.1 newtons. That's how I find tension. The mass density of strings, that's something that is usually given, but it doesn't have to be. It could be that we're given the tension and have to find mu, which would be the same process, right? Just right here, instead we'd be solving for mu, and we would say mu equals T over V squared, which is fine. I don't think that that's going to be causing problems for anyone. If you were wondering, because you might be curious, this one gets usually about 20 grams per meter. The D string is a little bit thicker. This one gets 30 grams per meter. The A string is usually something like 50 grams per meter, and the E string is usually something like 75 grams per meter. So you can figure out all the tensions, and you can figure out everything on these at this point.